Okay, this begins the second half of this unit on waves. Specifically, we cover sound for Honors Physics AB. This is Chapter 16. For Physics AB, this is Chapter 12. Okay, first of all, let's ask and answer the following question. What is sound? Sound is a three-dimensional longitudinal wave that propagates through a gas, such as the air, or a liquid, such as water. Three-dimensional longitudinal wave that propagates through a gas, such as the air, or a liquid, such as water. Okay, it's three-dimensional for the following reason. If you're in front of me, you can hear me. If you're to my right, you can hear me. If you're behind me, you can hear me. If you were up there, for example, you would be able to hear me. If you were down there, you would be able to hear me. So as my vocal cords vibrate against the air and then therefore produce a sound wave, that sound wave then propagates outwards as a spherical wave front, and it does so, of course, in three dimensions. Okay, now air is a particularly good elastic medium. It is a particularly good conductor of traveling oscillations, that is waves, and that's basically what a sound wave is. So for example, if I take this tuning fork here to produce a sound wave, I'm going to give it a whack in just a moment, and when I do, the tuning fork then vibrates back and forth at its fundamental frequency. In this particular case, it's 384 hertz. That is then therefore the frequency of the sound wave that it then produces. Now, when I do give this tuning fork a good whack, like so, you hear first of all a really high-pitched sound. That really high-pitched tinging sound comes from a really complicated waveform that appears here on each individual tongue of the fork, and it is of a very high frequency. But the fundamental frequency of the tuning fork is basically the fundamental frequency of a stick, for example, that is vibrating back and forth like so. When it does, in this particular case, it does so at a frequency of 384 hertz, and that then produces a sound wave of the exact same frequency. To give you a better idea as to what that sound is, here it is. It's that sound that you hear right there when I placed the tuning fork or pressed it up against the desk. How I use the desk to magnify the sound, we'll get to that a little bit later on. Okay, now at this point, what I invite you to do is to take a look at the short screencast video that I've posted for you on Schoology, where I show you a nice applet that then visualizes for us exactly what a sound wave looks like. So go ahead and pause this lecture here and take a look at that short screencast. It's only a couple of minutes long. Okay, now that you've seen that screencast, then let me go ahead and draw out the following for you. Okay, so let's say that right here is the source of sound, and the source of sound is a point source. So then therefore propagating outwards equally in three dimensions would be a set of spherical sound waves. Let's say that source there, that point source, is emitting sound at a constant frequency. So for example, it would be me standing here and just going, like so continuously if my voice was good enough to produce a single frequency. Don't worry, it's not. Therefore, from that point then, we would have simple periodic waves propagating outwards along spherical wavefronts. Okay, typically we draw the wave crest just like we do with two-dimensional circular waves from earlier in this unit. All right, so let's say that right here are some spherical wavefronts, like so. Like this. And if we say that the source has a constant frequency f, this then means that the distance from crest to crest here is equal to the wavelength lambda, or equivalently the distance from trough to trough, which I'm not going to bother to draw. Okay, and then the speed of the waves would then therefore be equal to the wavelength multiplied by the frequency. So once again, we have spherical wavefronts out here, for example, that then propagate in three dimensions, for example, through a gas such as the air, or through a liquid such as water. Okay, now that you've also seen that screencast, we can then visualize what the molecules themselves look like. So let's take a look at a small section here of these spherical wavefronts. What I'm going to draw out for you in terms of the molecules themselves is one complete wavelength. Once again, refer to that screencast that I posted for you on Schoology as well as I proceed. Okay, in order to draw one full wavefront, I'm going to draw the following. This right here is a simple diagram of the representation of the air molecules themselves. Like so. Now let's say that the wave itself is propagating in this direction with a speed v. What I've drawn here is one full wavelength. Okay, this portion of the wave, either here or here where the molecules are close together, this is referred to as a compression. And then mathematically we visualize that as corresponding to a crest. So the distance from crest to crest, for example, that would be one full wavelength. And then this portion of the wave here, where the molecules are kind of far apart from each other, this is referred to as a rarefaction. Here's how you spell that word. It's the same root word, for example, as in the term rarefied air. And then rarefactions then we picture as corresponding to troughs. So then therefore mathematically we visualize here one full wavelength in the following way. That is from crest to crest like so. And that then therefore is lambda. Okay, what I'm ignoring here and what the screencast animation is ignoring as well is the already random present motions of the molecules of a gas at some temperature. So if I'm talking about, for example, the temperature in this room, which is roughly 70 degrees Fahrenheit, this then represents the average kinetic energy of all the molecules of the air that make up this room. And then those molecules are moving around at various speeds, they're colliding with each other, colliding with objects in the room, and so on and so forth. The whole time that that is happening, as I speak to you, for example, we then have propagating through all of those air molecules, these spherical wavefronts. That's largely being ignored, for example, in the animation in the screencast, okay? All right, let me do some erasing here. Okay, a little bit about the speed of sound. The speed of sound is actually a pretty complicated function of a whole host of physical parameters that make up, for example, the air. It has to do with the temperature of the air pressure, its density, and so on. Same thing for water. Ultimately, the speed of sound is a pretty complicated function of those physical parameters. We're not going to derive it here in class by using fluid mechanics. It's actually quite difficult to do. But let me just give you a basic understanding as to what the numbers are for the speed of sound in air and, for example, the speed of sound in water. Okay, in air at room temperature, roughly 70 degrees Fahrenheit, and here at sea level, normal atmospheric pressure, the speed of sound in air is very nearly a constant. It changes slightly all the time as the physical parameters of the air itself changes, but for the most part, if you're talking about room temperature and at sea level, the speed of sound more or less is a constant, and it's about equal to 343 meters per second. Once again, it varies a little bit. Later on in this unit, I'll perform a simple demonstration that indicates how we would actually measure the speed of sound. It's actually quite easy to do. Okay, in water, however, because water is denser, the speed of sound is considerably greater. It's about 1440 or so meters per second. So this is one of the reasons why, for example, sounds sort of sound different when you're in water, like if you're in a swimming pool and you're beneath the surface of the water and you listen to something, for example, on the other side of the pool. It definitely sounds a little bit different than it would normally if the sound was transmitting through the air. And one of the reasons for that is because the speed of sound in water is considerably larger than it is in air. Certain frequencies of sounds will propagate unequally in the different media. So for example, high frequency sounds propagate really well in water, but low frequency sounds definitely do not. So then therefore, sometimes when you're in water and you listen to, say, somebody on the other side of the swimming pool tapping the ladder or something like that, it's usually very easy to hear, okay? Okay, next a little bit about frequency. Okay, the word frequency here, of course, is a physical parameter, and it refers to the number of waves per second. It's measured in terms of hertz, but the corresponding terms that we use to describe our physiology, in other words, our senses, our sense of hearing, are the terms pitch and tone. So pitch, and also sometimes tone, especially in a musical connotation. These are physiological terms, that is, it describes our senses. That correspond to the physical quantity frequency. In other words, what we think of as very low-pitched tones, that corresponds to small frequencies. Okay, very high-pitched tones, that corresponds to large frequencies. There is quite a wide range of frequencies. This is referred to as the audio spectrum that human beings can hear. That range of frequencies in the audio spectrum that we can hear starts at around 20 hertz or so for the lowest pitched tones that we can hear, up to about 20,000 hertz or so for the highest pitched tones that we can hear. I've filmed for you a demonstration of the audio spectrum. I invite you to pause this film here and then go ahead and take a look at that short demonstration. It's only a couple of minutes long. However, one of the things I noticed about that demonstration after I filmed it is that unfortunately towards the end of the film you can't hear the low-pitched sounds very well. The microphone, unfortunately, my phone did not pick that up very well. At any rate, however, go ahead and look and listen to that demonstration right now, please. Okay, so the audio spectrum, as you just saw and heard, goes from about 20 up to about 20,000 hertz. Like so, and that then corresponds to the range of frequencies, basically, that human beings can hear. It varies, of course, a little bit from person to person. Okay, another thing that I can mention here also about frequencies before I continue is the following. Have you ever listened to the sound of your own recorded voice? And you perhaps have found the sound of your own recorded voice to be somewhat annoying. It's a higher pitched sound than what you would normally hear as if you were just speaking and listening to your own voice. Well, I hate to tell you this is how everybody else hears your voice. And the reason for that is because when you listen to the sound of your own voice as you speak, you're not just listening to sound waves that are propagating through the air, you're also listening to sound waves that are propagating through your skull. Literally, your head is rattling as you speak to yourself. So try the following at home. Go ahead and take your hands and kind of place them on your jaw and place them on your cheeks like so, and then just go, ah, like that. And when you do, you can basically feel your jaw and you can feel your face vibrating a little bit. So when you listen to some of those sounds as they propagate through your head to your ear, they are of a lower pitched variety than what normally propagates through the air itself. So yeah, I hate to tell you this, when you listen to the sound of your own recorded voice and you think to yourself that it sounds somewhat annoying, well, that's how everybody else hears you, okay? Okay, a couple of terms here that I want to define for us that are a little bit confusing because they all contain the same word sonic. Okay, let me describe to you, first of all, what is meant by supersonic and then subsonic. Okay, these two terms here refer to the speeds of sources of sound. A source of sound that is supersonic is traveling at a speed that is greater than the speed of sound. So the source of sound is at a speed greater than the speed of sound. And then secondly, the term subsonic. This refers to a source of sound that is traveling at a speed less than the speed of sound. So the source of sound is at a speed less than the speed of sound. Okay, and then two other terms which sound pretty similar to each other, once again, each containing the word sonic. They are ultrasonic and infrasonic. Ultrasonic and infrasonic. Ultrasonic and infrasonic refers to frequencies. First of all, ultrasonic frequencies are frequencies that are above the audible spectrum range of human hearing, that is, sounds that are above 20,000 hertz. Dogs, for example, could hear well into the ultrasonic portion of the audio spectrum. This is, for example, typically where dog whistles operate. Dog whistles operate at frequencies that are in the neighborhood of about 40,000 hertz or so. Bats, for example, could also hear well into the ultrasonic range. So ultrasonic refers to frequencies above 20,000 hertz. Whereas the word infrasonic, that then refers to frequencies that are less than 20 hertz, the lower end of the audible spectrum range of human hearing. A nice example of infrasonic frequencies would be seismic waves. You can't hear seismic waves because the frequencies of seismic waves are less than 20 hertz. They're in the neighborhood of like 5 hertz or so. So infrasonic refers to frequencies less than about 20 hertz. So these four terms here are obviously pretty similar to each other because each one contains the word sonic, but they have different meanings, okay? All right, this concludes here part 1 of today's lecture. Go ahead and stop the film here. I will then start part 2 in just a few moments. Thank you.